The universe is 95% unknown. Dark matter and dark energy make up everything we can't see, can't touch, and can't explain, while the 5% we understand is just the leftovers. And those invisible forces aren't the only thing keeping physicists awake at night. From vanishing antimatter to signals that matched alien predictions perfectly, I'm breaking down the 8 biggest unsolved mysteries in space that science still can't answer, starting with the invisible scaffolding holding the entire cosmos together. Dark matter. Something is out there and we have zero idea what it is. Dark matter makes up roughly 85% of all mass in the universe, yet it doesn't emit, absorb, or reflect light. We only know it exists because without it, galaxies would literally tear themselves apart. Here's where it gets weird. In 1933, Fritz Zwicky noticed galaxies in the Coma cluster were moving way too fast to be held together by visible mass alone. He called the missing substance dark matter, and everyone ignored him for 40 years. Then Vera Rubin showed up with data nobody could dismiss. Starting in 1968, she studied spiral galaxy rotation curves and found something that broke physics. Stars at the outer edges of galaxies were orbiting just as fast as stars near the center. That's impossible unless there's 5 to 10 times more mass than we can see. By 1980, she'd proven this pattern held for 21 different galaxies. Eventually, she studied over 75 galaxies, and every single one showed the same thing. The most dramatic proof came in 2006 with the Bullet Cluster. 2 galaxy clusters collided 3.8 billion light years away, and NASA's Chandra X-ray Observatory caught what happened. The hot gas slowed down from the impact, but gravitational lensing showed the majority of mass passed straight through, completely separated from the gas. That invisible mass was dark matter, so scientists have been hunting for dark matter particles for decades using massive underground detectors. The LX Zeppelin experiment sits a mile underground in South Dakota with 7 tons of liquid xenon. In December 2025, they released results from 417 live days of data collection. The result? Nothing. 0 particles detected. But they're now over 3 million times more sensitive than first-generation experiments, which means if WIMPs exist in certain mass ranges, we should have caught them by now. In November 2025, a University of Tokyo professor claimed he found possible evidence in Fermi telescope data, but most scientists aren't buying it. After 90 plus years and billions of dollars in experiments, we've never directly detected a single dark matter particle. We might be looking for the wrong thing entirely, but at least dark matter just sits there. The next mystery is actively ripping the universe apart. Dark energy. In 1998, 2 teams of scientists discovered something that shouldn't be possible. The universe's expansion isn't slowing down like everyone expected. It's speeding up, and it's been accelerating for the last 5 billion years. The Supernova Cosmology Project, led by Saul Perlmutter and the High Z Supernova Search Team, led by Brian Schmidt and Adam Rees, were both studying distant exploding stars called Type 1 a supernovae. These explosions are so consistent they work like cosmic measuring sticks. But when both teams analyzed their data, they found the supernovae were roughly 25% fainter than they should be, meaning they were farther away than a decelerating universe would allow. Something was pushing space-time apart faster and faster. They called it dark energy, and all 3 scientists won the 2011 Nobel Prize in Physics for the discovery. Here's the problem. Dark energy makes up about 68% of the universe, but we have no idea what it is. Its density is absurdly low, roughly 7 times 10 to the negative 30th grams per cubic centimeter. But because it fills all of space and doesn't dilute as the universe expands, it dominates everything. And quantum theory predicts vacuum energy should be 10 to the power of 120 times larger than what we observe. This is literally called the vacuum catastrophe, and it's the most embarrassing prediction in the history of physics. But here's where it gets complicated. There's a massive crisis happening right now called the Hubble tension. Measurements of the universe's expansion rate from nearby supernovae give you about 73 kilometers per second per megaparsec. Measurements from the early universe's cosmic microwave background give you about 67.4. That gap is 5 sigma, which means it's way too large to be random chance. In February 2024, James Webb Space Telescope observations confirmed the discrepancy at 8.2 sigma confidence. Something fundamental is wrong with our models. Then in March 2025, the Dark Energy Spectroscopic Instrument dropped a bomb. After analyzing 14 million galaxies, they found dark energy might not be constant. It was stronger in the past and appears to be weakening today. If that's real, it overthrows 25 years of cosmology. The fate of the universe depends on what dark energy does next. If it stays constant, we get a cold, empty, big freeze. trillions of years from now. If it strengthens, we get a big rip that tears apart atoms in 22 billion years. If it weakens enough, the universe could even reverse into a big crunch. And if you think missing 95% of the universe is disturbing, wait until you hear about the paradox that asks why we're completely alone. The Fermi paradox. The universe should be crawling with aliens, but we've never found a single trace of them, and that makes zero sense. In the summer of 1950, physicist Enrico Fermi was walking to lunch at Los Alamos National Laboratory with colleagues. They'd been joking about a New Yorker cartoon showing aliens stealing trash cans. Then mid-meal, Fermi suddenly blurted out, "Where is everybody?" Everyone at the table immediately understood he meant extraterrestrial life. As one colleague recalled, Fermi then rattled off probability calculations and concluded we ought to have been visited long ago and many times over. The numbers make this worse every year. The Milky Way contains 200 to 400 billion stars. The observable universe holds roughly 2 trillion galaxies and about 10 to the 24th total stars. NASA's Kepler and TESS missions have confirmed over 6,100 exoplanets as of late 2025, and research suggests at least 25% of stars host Earth-sized planets in habitable zones. That means 5 to 10 billion potentially habitable worlds in our galaxy alone. The universe is 13.8 billion years old, and the Milky Way has existed for over 13 billion of those years. Plenty of time for civilizations to arise and spread. In 1961, astronomer Frank Drake wrote an equation to frame the problem. The Drake equation estimates the number of communicative civilizations by multiplying factors like star formation rate, fraction of stars with planets, and how long civilizations survive. We now know several variables are favorable. Nearly all stars have planets, but the critical unknowns remain completely unconstrained. How often does life arise? How often does it become intelligent? How long do civilizations last? The proposed solutions are as varied as they are unsettling. The Great Filter Theory says somewhere between dead matter and spacefaring civilizations lies an almost impossible step. If the filter is behind us, we're lucky. If it's ahead of us, we're doomed. The Dark Forest Theory says the universe is a dark forest where every civilization is a silent armed hunter, and revealing yourself invites destruction. The zoo hypothesis says advanced civilizations deliberately leave us alone, treating Earth like a nature preserve. The rare Earth hypothesis says Earth's conditions are extraordinarily unusual. SETI has been listening since 1960. The most ambitious effort, Breakthrough Listen, launched in 2015 with $100 million over 10 years. It's surveying 1 million nearby stars and 100 nearby galaxies. In April 2025, JWST researchers detected possible chemical signatures of dimethyl sulfide on exoplanet K2-18b, a molecule produced only by life on Earth. The detection needs more confirmation, but it represents the strongest biosignature candidate ever found, which makes the silence even more disturbing. But at least the Fermi paradox is a question. The next mystery is something we can actually detect, and it makes absolutely no sense. Fast radio bursts. In 2007, Duncan Lorimer and undergraduate David Narkovich were reviewing archival data from Australia's Parkes Radio Telescope when they found something impossible. A signal recorded on July 24, 2001, but unrecognized for 6 years. It lasted less than 5 milliseconds, came from billions of light years away, and was so powerful it saturated the telescope's instruments. They discovered the first fast radio burst. Nobody believed them at first. Similar signals were later traced to researchers opening microwave oven doors at the observatory. But when 4 more FRBs were confirmed in 2013, the field exploded. Over 5,000 FRBs have now been detected, the vast majority by Canada's CHIME telescope. 4 massive cylindrical antennas near Penticton, British Columbia, that scan half the sky daily. CHIME detects roughly 2 FRBs per day. Bright FRBs are estimated to occur somewhere in the sky about 800 times daily. Here's what makes them terrifying. A typical FRB releases as much energy in a millisecond as the sun emits in 3 days, yet the signal reaching Earth is about 1,000 times weaker than a cell phone on the moon. The mystery deepened when FRB 20121102A, discovered at Arecibo in 2012, was found to repeat, proving not all FRBs come from one-time cataclysmic events. It was traced to a dwarf galaxy 3 billion light-years away. Even stranger, FRB 20180-916b repeats on a precise 16.35-day cycle, suggesting orbital or precession mechanics in the source. The breakthrough came on April 28, 2020, when magnetar SGR 1935 + 2154, a hypermagnetic neutron star 30,000 light years away in our own galaxy produced an FRB like a burst. Simultaneous X-ray bursts were caught by 4 satellites. This was the first FRB-like signal from within the Milky Way, and the first linked to a known source, establishing that magnetars can produce FRBs. But then came January 2025's curveball. FRB 202402098 was traced to the outskirts of an 11.3 billion year old dead elliptical galaxy, 130,000 light years from the galaxy's center and 2 billion light years from Earth. Dead galaxies shouldn't produce young magnetars. This discovery, published in the Astrophysical Journal Letters, challenges the entire framework. The leading explanation is that the magnetar formed through exotic channels in a globular cluster, possibly from a white dwarf collapse or neutron star merger. Over 50 theories for FRB origins have been proposed, and every time scientists think they've figured it out, a new detection breaks their model. But at least we can detect fast radio bursts. The next mystery is something so massive it's pulling our entire galaxy through space, and we literally cannot see what it is. The Great Attractor. The Milky Way, along with hundreds of thousands of other galaxies, is hurtling through space at roughly 600 kilometers per second. That's about 2.2 million kilometers per hour. And we're all being pulled toward a single region of the cosmos that we cannot see. The anomaly was identified in the 1970s and confirmed between 1986 and 1988 by a team of 7 astronomers dubbed the Seven Samurai. By compiling data on over 400 elliptical galaxies, they revealed a coherent bulk flow of about 600 kilometers per second toward a point in the direction of the Centaurus constellation, located roughly 150 to 250 million light years away. The mass required to produce this pull? Approximately 10 to the 16th solar masses. That's equivalent to tens of thousands of Milky Ways. Here's the maddening complication. The Great Attractor sits behind the plane of our own galaxy, in what astronomers call the zone of avoidance. The Milky Way's dense concentrations of dust, gas, and billions of stars block visible light from that direction. It's like trying to spot a distant bonfire while staring into a floodlight. Astronomers have partially pierced this veil using X-ray telescopes, infrared surveys, and radio observations. Behind the zone of avoidance, they found the Norma cluster, a massive galaxy cluster with a dynamical mass of roughly 10 to the 15th solar masses, containing 296 plus confirmed galaxies. But Norma alone isn't massive enough to explain the full pull. Farther beyond lies the Shapley supercluster at about 650 million light years, one of the largest galaxy concentrations in the observable universe, adding its own gravitational tug. In September 2014, a landmark Nature cover story by Brent Tully and colleagues mapped our home supercluster for the first time, naming it Laniakea, Hawaiian for immense heaven, spanning 500 million light years and containing about 100,000 galaxies with a combined mass of roughly 10 to the 17th solar masses. Laniakea revealed the Great Attractor as its gravitational focal point, a vast valley into which galaxies flow like water in a watershed. The Wallaby Radio Survey in 2024 detected 27 new galaxy counterpart in the zone of avoidance, and 2025 studies using digital twin simulations are refining our understanding. Yet predicted velocities from models still fall short of observations by up to 20%, and the dark matter distribution, likely dominating the mass, remains unmapped. So we know something enormous is pulling us through space at millions of kilometers per hour. We know roughly where it is. We've mapped some of the structure, but we still can't see the thing itself, and our models can't fully explain what we're observing. At least the Great Attractor is just pulling us. The next mystery is why anything exists at all. Matter versus antimatter. The Big Bang should have produced exactly equal amounts of matter and antimatter. When these meet, they annihilate completely into pure energy. If the amounts had been perfectly balanced, the universe would contain nothing but a diffuse soup of photons. No atoms, no stars, no planets, no you. Instead, for reasons no one can explain, there was a tiny imbalance, roughly one extra matter particle for every billion matter-antimatter pairs. That one in a billion surplus is literally everything we see. Antimatter was predicted by Paul Dirac in 1928 and confirmed in 1932 when Carl Anderson discovered the positron, the anti-electron, in cosmic ray photographs. He won the 1936 Nobel Prize for it. Antimatter is real, well understood, and routinely produced in particle accelerators. The mystery isn't what it is, it's where it went. The first clue came in 1964 when James Cronin and Val Fitch at Brookhaven National Laboratory discovered that nature treats matter and antimatter slightly differently, a phenomenon called CP violation. They observed unusual decays of neutral kaons that shouldn't happen if matter and antimatter were perfect mirrors of each other. This earned them the 1980 Nobel Prize. In 1967, Soviet physicist Andrei Sakharov identified three conditions necessary for a matter-dominated universe to emerge: baryon number violation, CP violation, and departure from thermal equilibrium. Here's the problem. Known CP violation in the Standard Model is far too small, by many orders of magnitude, to explain the observed asymmetry. Something beyond known physics must be responsible. The hunt continues at CERN with extraordinary precision. The ALPHA experiment has trapped anti-hydrogen atoms and measured their gravitational behavior, confirming in 2023 that antimatter falls the same way as matter. The BASE experiment has compared proton and antiproton properties to within 16 parts per trillion, the most precise test of matter-antimatter symmetry ever. In 2025, BASE achieved the first coherent spectroscopy with a single antiproton spin, named one of physics world's top 10 breakthroughs of the year. On the International Space Station, the AMS-02 detector, a 7.5-ton instrument delivered by the Space Shuttle in 2011, has analyzed over 230 billion cosmic ray events searching for primordial antimatter. In 2024, the team revealed they detected traces of anti-helium nuclei in cosmic rays, potentially revolutionary but still under investigation. The landmark result of 2025 came on March 21st when the LHCb collaboration announced the first observation of CP violation in baryon decays, a 5.2 sigma discovery involving over 80,000 beauty lambda baryon decays. Published in Nature in July 2025, this measured a CP asymmetry of 2.45%. But here's the kicker. As LHCb spokesperson Vincenzo Vagnoni noted, this is still consistent with standard model predictions and remains far too small to explain why matter won. There should be a new class of particles, Vagnoni said, that exhibit a much larger amount of this behavior. After decades of experiments, we still don't know why you exist instead of having annihilated into energy 13.8 billion years ago. But at least the matter-antimatter mystery is about the past. The next paradox threatens to break physics itself, the black hole information paradox. Here's a paradox that has consumed theoretical physics for 50 years. Quantum mechanics says information can never be destroyed, but black holes appear to destroy it completely. One of these pillars of physics must be wrong, and figuring out which one could unlock a theory of everything. The trouble started with Stephen Hawking's landmark 1974 Nature paper, which showed that black holes aren't truly black. They emit faint Hawking radiation through quantum effects near the event horizon. This radiation causes black holes to slowly evaporate over incomprehensibly long timescales. Here's the critical problem. Hawking argued this radiation is perfectly thermal and random, carrying zero information about what fell in. Two black holes of identical mass formed from entirely different objects would emit identical radiation. When evaporation completes, the information has been erased, a direct violation of quantum mechanics' foundational principle of unitarity. The paradox is sharpened by the no-hair theorem. Classical black holes are described by only three numbers: mass, charge, and spin. As physicist John Wheeler put it, black holes have no hair. Everything else about the unfalling matter, its composition, structure, history, appears irretrievably lost. The debate became a literal wager. On February 6, 1997, Hawking and Kip Thorne bet against John Preskill, all at Caltech, that information is permanently destroyed. The stakes? An encyclopedia from which information can be retrieved at will. On July 21, 2004, Hawking publicly conceded in Dublin, presenting Preskill with a copy of Total Baseball. Thorne declined to concede. Theoretical proposals have proliferated. The holographic principle, proposed by Gerard A. T. Hooft in 1993 and Leonard Susskind in 1994, suggests all information within a volume of space is encoded on its boundary surface. Juan Maldasena's 1997 ADS-CFT correspondence provided a mathematical framework strongly implying information is preserved. Then in 2012, the firewall paradox argued that preserving information requires the event horizon to become a lethal wall of radiation, violating general relativity's equivalence principle. The most celebrated breakthrough came in 2019 to 2020 when two independent groups showed that semi-classical gravity calculations could reproduce the page curve, the predicted information return trajectory, through entanglement islands. Regions inside the black hole are mathematically reassigned to the radiation system after the midpoint of evaporation. This was hailed as the biggest advance in 50 years. The calculations confirmed information escapes but didn't specify the physical mechanism. In 2024 to 2025, researchers have explored quantum hair corrections suggesting Hawking radiation subtly encodes information. In December 2024, work proposed that quantum correlations in spacetime itself may resolve the paradox, potentially leaving signatures in gravitational waves. But here's where we are. After 5 decades of work by the brightest minds in physics, we still don't know if information is preserved, how it escapes, or what this means for the laws of physics. The paradox remains unsolved, and if you think that's frustrating, the final mystery is a signal that matched every prediction for alien contact, then vanished forever. The WOW signal. At 10:16 p.m. on August 15, 1977, Ohio State University's Big Ear radio telescope captured a signal so extraordinary that volunteer astronomer Jerry Eman, reviewing the printout days later, circled the data in red ink and scrawled a single word in the margin. Wow. The signal lasted exactly 72 seconds, the maximum window for any celestial source given the telescope's fixed orientation. It rose for 36 seconds, peaked at roughly 30 times background intensity, then fell for 36 seconds, perfectly matching the telescope's antenna pattern for a deep space source. Its frequency was 1420.4556 MHz, within 50 kHz of the hydrogen line, the frequency that physicists Morrison and Cocconi had argued in 1959 would be the logical choice for interstellar communication. It was extremely narrowband, about 10 kHz, confined to a single receiver channel, and came from the direction of the constellation Sagittarius. In short, it matched every theoretical prediction for what an alien signal would look like, and it has never been detected again despite dozens of follow-up attempts over nearly 5 decades. In 2017, Professor Antonio Paris proposed the signal came from hydrogen surrounding a comet, but the hypothesis was widely rejected. Eman himself argued against it. Critics noted the signal was too strong and too brief for a cometary origin, and the paper wasn't published in a major astrophysics journal. In 2024, a more compelling hypothesis emerged when Abel Mendez and colleagues found 8 WOW-like signals in Arecibo Observatory archival data, all near 1,420 MHz but 50 to 100 times weaker. Their proposed mechanism is that a magnetar flare striking a cold hydrogen cloud produces intense, brief superradiance at the hydrogen line frequency. Penn State SETI astronomer Jason Wright noted skeptically, he's suggesting a phenomenon that has never been observed. The WOW signal isn't the only mysterious detection. Oumuamua, the first confirmed interstellar object discovered in October 2017, exhibited unexplained non-gravitational acceleration that Harvard's Avi Loeb controversially attributed to alien light cell technology. Tabby's star, discovered in 2015, showed inexplicable brightness dips of up to 22% that briefly fueled alien megastructure speculation before dust was identified as a likely cause. And BLC-1, a tantalizing 2019 signal from Proxima Centauri, detected by Breakthrough Listen, fooled every standard SETI screening algorithm before being identified as human radio interference in 2021. Nearly half a century on, the WOW signal remains the single strongest candidate detection in SETI history. Every proposed natural explanation has significant weaknesses. Its one-time nature makes it impossible to verify or dismiss. It embodies the core tension of the search for extraterrestrial intelligence. The universe looks like it should be full of life. One signal matched what contact should look like, and then silence. These 8 mysteries share a striking common thread. The evidence is overwhelming, but the explanations remain elusive. We can map dark matter's gravitational influence across billions of light years, but can't catch a single particle of it. We can detect millisecond radio bursts from halfway across the cosmos, but keep discovering sources that break our best theories. And 95% of the universe operates by rules we haven't discovered yet. The answers, when they come, won't just solve individual puzzles. They'll rewrite our understanding of reality itself. If you enjoyed this video and want to see more, click the video on the screen now.